Hi, this video is a lecture video about linear algebra course. So today we're going to talk about eigenvalues property of special matrices in the group of symmetric, unitary, idempotent, projection, orthogonal projection, and nilpotent and positive definite matrices. I select this group of matrices because it finds a lot of applications in engineering, and we're going to extend the basic property from what we learned about eigenvalue. Okay, so refer to our prior knowledge about eigenvalues. If A is a square matrix, okay, we call X eigenvector and we call lambda eigenvalue. So eigenvalue and eigenvector satisfy these eigenvalue equation. Okay. We also learn, okay, from linear algebra that A has eigenvalue decomposition. A equals T D T inverse. Okay, where the matrix T here contain T1, T2, Tn. These column vectors are eigenvectors of A. Okay, D is a diagonal matrix, D1, D2 until Dn. Okay, and the diagonal entries here are eigenvalues of A. So this is what we learned from eigenvalue property. So today, okay, I'm gonna explore each type of matrices and to see what special characteristic of eigenvalue and eigenvectors from a particular type of matrices. So the first one we're gonna talk about symmetric matrix. So everyone here know the definition that a symmetric matrix is a matrix that A equals to A transpose, which means if we use a notation that A has the entry Aij, it means that Aij equals Aji. Okay. So I'm gonna state I'm gonna explain later about the property and give the proof. But let's take a look at this statement. Okay, the statement is that if A is a symmetric matrix, it happens to be that all the eigenvalues are real. Okay, what we learned from linear algebra is that even though A is is real, all the entries are real, it is possible that the eigenvalues of A can be complex, and when it's complex, it would occur in a complex conjugate pair. Okay, for example, this is a matrix A that the eigenvalues are complex. Okay, minus plus and minus j. Okay, so this is one special property about symmetric matrices. All the eigenvalues are real. Okay, second of all, the eigenvectors are orthogonal. Okay, when it's orthogonal, and that's why we're gonna have the last property. Okay, so from these three properties, it will allow us to analyze, derive some useful results in the future. So I'm gonna show why these properties are true. Okay, first of all, all the eigenvalues of A symmetric matrices, they are real. So in order to do this, I would like to explain a little bit about the notation, because when you deal with the eigenvalues, eigenvectors of a matrix, okay, when lambda can be complex, all right, it would be possible that your eigenvector can be complex too. Okay, so I would like to introduce this notation. So if X is is a complex vector, usually we know that transpose is just the operation that change from row to column. Okay, and our notation is that when we talk about a vector is always column vector. Okay, so but when you deal with complex matrices, complex vector, I would like to introduce this notation that star. The notation is that the star is called Hermitian conjugate. It means that you make the transpose and take the complex conjugate pair. Okay, which means X star or X bar transpose is going to be X1 bar, X2 bar, dot, Xn bar. Okay, this notation. Very simple. Everyone should know that X star X then is going to be X1, the modulus of X1 square, modulus of X2 square, dot, modulus of Xn square. And this is what we know by the common notation that this is called the true norm of a vector. Okay, so let's go. Now I would like to show that the eigenvalues of symmetric matrices can be real, only it cannot be complex. Okay, so I start with a standard equation, Ax equal lambda x. Everyone knows x eigenvector, lambda is eigenvalue. Okay, next, what I'm gonna do is that I'm gonna remember that this is a vector equation. Okay, vector equation, which means the vector ax is this, lambda is just a scalar, the vector x is this. Okay, I'm just gonna multiply x star on the left hand side. Everyone should know that, the reason why I can do this because x star is gonna be, a row vector. Okay, and then then this becomes scalar, right? It becomes scalar. Then I take the complex conjugate pair on this scalar quantity. Oh, sorry, I should yes. Hold on. Okay, this is a scalar. This is a scalar. Okay, then what do I do next is that I take the complex conjugate on both sides. Remember that this is a scalar. If I take the star, it just means that I take the complex conjugate pair. Okay, but then from the left hand side, the Hermitian conjugate operation, it just works like transpose operation, because which means a b star is going to be b star a star. Okay, then from here what I get is that x star a star x equals lambda bar x star x, which is lambda bar norm of x squared. Okay, everyone shouldn't be confused on the fact that lambda star is just going to be lambda bar, right? Because lambda is a scalar. Okay, then from the next step, on the left hand side, what you get is x star a star x. Now we're going to use the fact that the matrix A here is symmetric. It is symmetric, and actually we are taking a look particularly on real matrices, which means which means A star equal to A transpose and equals to A. This is by assumption. So from here we get A x star A x equals lambda bar norm of x squared. Okay, so compared to the first one, this is where we start. X star a x equal to lambda x star x and equals to lambda norm of x squared. So if you equate 1 and 2, what you're gonna get is that 0 equals lambda minus lambda bar multiply norm of x squared. Okay, of course this guy is non-zero because x is an eigenvector. This implies lambda equals lambda bar, and that shows that the eigenvalues of symmetric matrices are real. Next property, next property, which is also as important as the first one. All the eigenvalues are orthogonal. Let's recall what does it mean by orthogonal. We use this notation. A vector x and y are orthogonal when the inner product between x and y is 0. Okay, where the angle between these two vectors is 90 degrees. Okay, now to show that eigenvectors of symmetric matrices are orthogonal, so we're gonna first start with the setting that suppose you have two eigenvectors that satisfy eigenvalues equation, x1, with the lambda 1, ax2 equals lambda 2 x2. Okay, this is given. Okay, and we're going to show that x1 and x2 are orthogonal. Okay, we're going to rule out the case where eigenvalues can be repeated. That's a special case. We can handle that, but in this simple proof, I'm just going to show that for the case that lambda 1 is not equals to lambda 2. Okay, now let's see. This is given. From the previous fact that all the eigenvalues of A are real, it can also it further imply that we are allowed to choose a real eigenvector, right? Because everyone knows that when you have an eigenvector, you can scale by a scalar. That scalar can be real, can be complex, and the scaled vector is also eigenvector, right? If x is eigenvector, alpha x is also an eigenvector. But then when you have real eigenvalues, you don't need to choose x to be complex because it's more complicated in calculation. So it's very normal that we're gonna assume that these x1 and x2, which are eigenvectors of symmetric matrices, are chosen to be real. Then now let's see. Hold on. I'm going to call this equation 1, call this equation 2. Okay, there's a little bit delay on the screen. Okay. Now I'm going to multiply x2 transpose, all right, on equation 1. Remember again that eigenvector, eigenvalue equation is a vector equation. Okay, I multiply, like I perform an inner product with a vector x2 on both sides. That's gonna turn into a scalar. This guy is scalar. All right. Now this is from equation 1. On the following results, I'm gonna multiply x1 transpose, make the inner product with x1 on equation 2, and this is what I get. All right. Now let's take a look at equation 3 and 4. How are they related? Okay, you're gonna see that on the left hand side of equation 3 and 4, they are basically the same quantities, right? Because if this guy is scalar, if you transpose, it's just gonna be the scalar, right? And it happens to be x1 transpose, A transpose, x2. But A here is symmetric, so this guy equals to x1 transpose A x2. Which means if you subtract equation 4 from 3, you're going to get 0 equals to lambda 1 minus lambda 2, x2 transpose x1. And again, we use the fact that, of course, inner product between x1 and x2 equals inner product between x2 and x1 because x1 and x2 are real. All right. On this line, on this result, what can we say? What can we say? When we assume that lambda 1 is not equal to lambda 2, right? This guy is non-zero, which means which means x2, inner product between x2 and x1 must be 0, which means x1 is perpendicular to x2. And that's why we get the second result. All the eigenvectors of A are orthogonal. Of course, when we take a look at the eigenvalue decomposition, where we remember that, recall that for any matrices, okay, that are diagonalizable, all right, the matrix A will admit this eigenvalue decomposition, okay, but then we just have proved that all the eigenvectors of A are orthogonal. So the matrix U here is a matrix that contains eigenvectors of A. All right. When Ui and Uj are orthogonal, okay, it means that U transpose or U transpose U. Let's take a look at U transpose U. U transpose U is going to be U1 transpose, U2 transpose, dot, 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 UN transpose. Okay. And then this is a multiplication of two matrices, all right? If I multiply, then we're going to get U1 transpose U1, U1 transpose U2, dot, 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 U1 transpose UN. Okay. And you're going to get this. All the diagonal terms are actually the inner product of Uj and Uj itself. And remember that you can scale the eigenvectors by any scalar. So let me assume that you can just scale it until you can just scale it so that the Ui transpose Ui is the norm of Ui square and equals to 1. You just normalize it, normalize the eigenvector. Okay, so the diagonals are 1. Okay, this is what you choose, what you intend to do it. Normalize eigenvector so that the norm is 1. But then on the off diagonal terms, this is what you have from the second results, that is going to be 0 because Ui and Uj are orthogonal. And that shows that, you know, when A is symmetric, eigenvectors are orthogonal. U transpose U equals I. Okay? U equals U equals I, which means U transpose U equals I. It means U inverse is U transpose. That's why in for symmetric matrices, the eigenvalue decomposition reduced to the form that, you know, A equals U D U transpose. Okay. From these results, it implies a lot of useful, well-known results, well-known mathematical inequality. I'm just gonna explain one inequality that we will refer to this inequality all the times. All right. Let me make a note here that from the previous property, that when a matrix U have satisfied this condition, U transpose equals to U transpose U equals I, it is called a unitary matrix. And we're going to explain this shortly after we finish about symmetric matrices. Okay, now I would like to derive one mathematical inequality that refer to symmetric matrices. All right, here X transpose AX. Okay, if I know that A is symmetric, then I know that A admit this decomposition U D U transpose X, where the U has the property that U transpose U transpose U equals I. All right, equal U transpose. Okay, from here, U is a matrix. All right, X is a vector. So if I call this guy a vector Y, right? Matrix times vector is a vector. This guy would be Y transpose. So basically, it just this on the left hand side, this is called quadratic function in X, because you see X appears in the expression like quadratic function. All right, this is, we call it quadratic form in X. When A is symmetric matrices, you can just change the expression in terms of vector Y, where Y relates to X by this equation. Okay, but then why this transformation useful? Because Y transpose is going to be Y1, Y2, Yn, right? D1, D2. Now D is diagonal, and that's a good part of it. When you have quadratic form in a vector Y, the expression of the quadratic form turns out to be very simple, because you can just multiply it out, and this is you're gonna get. Okay. Then next, or you can write it in a summation format, is DIYI square. All right. Now, when we have this, all right, it means that quadratic form in X can be written as sum square in vector Y. Okay. Next, what do we know about this quantity, this non-negative term? If I'm trying to find a lower bound of this quadratic form, okay, of course it can be it will be bounded above by the maximum of di, right? Multiply y1 square dot yn square. And of course, it can be bounded below by the minimum of di, with the same thing. Okay, I hope everyone agrees on this, right? You have coefficient of d1, d2, dn, okay? So you just pick the maximum one. That one, when it's multiplied with all the entries here in the sum, it will provide an upper bound, right? But then what is the maximum of di? Is actually the lambda max of A, all right? And the sum of y is actually the norm of y. So I'm just change the format. Mean of di is actually the lambda mean of A, right? And multiply by the norm square of y. And then this is a very important inequality, but I'm not finished yet. I'm just gonna further, derive back derive it back in the form of vector x. When y equals to u transpose x, okay, now let's compute the two norm of y. Two norm of y is y transpose y. And of course, when you just plug it in, it's x transpose u transpose x. Okay, but this u is special because this u satisfies the property that u transpose is I. So this reduces to x transpose x, which is the norm of x squared. Very, very important result. If y and u relates by unitary transformation, okay, the norm of y, the norm of y doesn't change. The norm of x and norm of y are equal, preserved by the norm is preserved by unitary transformation. So here, and from the beginning that X transpose X equals this, so we can conclude the result that when you have quadratic form of X, it will be you're gonna always have these two inequality, that quadratic form of X, parameterized by the matrix A, is bounded above by lambda max of A multiplied with the two norm of X, and bounded below by the minimum eigenvalues of A multiplied by the norm of X. Okay. It might be questionable where, when and where we're gonna apply these results, but let's take a note here, and later in the analysis or in the problem exercise, you might come back to this inequality later. Okay. So the three properties of symmetric matrices we have shown completely now. Next, let's take a look at unitary matrices. Okay, unitary matrices. I'm just gonna focus on real matrices, right? The definition is that U transpose U equals U transpose equals to I. Okay, actually we see previously that from this condition, U transpose equals I. If you partition U into, column vector, all right. Sorry. If we take a look at this equation, U transpose U equals I. It just basically means UI transpose UJ must be 0. Okay, which means for a matrix to be unitary, it means that the column vectors must be orthogonal. And this is an example. Okay, the example in the orange color find many applications, especially in mechanical engineering. You may have seen it before. This is called rotation matrix. What this metric does is that if you have a vector X, all right, and then, sorry, X1 next to, if you're in R2, if you have a vector X, if you multiply X with this guy, with this orange matrix, this is what we call rotation, it will basically give you a vector Y, but the result is that the vector Y, where Y and X align with the angle of theta, where theta is this theta in the matrix. It's a rotation because norm of vector Y and norm of vector X will be equal. It just differs by the angle only. Okay. Okay. The property that when you multiply X by a unitary matrix U, or it can be U or U transpose, the result is that norm of Y equals to the norm of X. Okay, we just proved previously on this page. Okay, and this is the result. I state here again. Okay, a unitary matrix is always invertible because from the definition itself, if you have the property that U transpose equals I, it basically means that you have just found a matrix that multiply U on the right hand side and equals to I. And at the same time, you just have found some metric that multiply U on the left-hand side at equals to I. This is just proof that U is always invertible. And what we learned from eigenvalues subject is that when a matrix is always invertible, it means that 0 cannot be an eigenvalues of this matrix. Okay, now let me make one question, ask one question. If we know from this property, okay, by the definition, I would like you to take a look at the determinant of this matrix. What is it? Okay, here the student, any student can pause the video when I raise a question. Just take a moment and keep some time, make some time to think about the answer. Pause the video, think about the answer, and come back again. Okay, what is the determinant of U? All right, everyone know that U transpose equal to the determinant of I, right? So, and of course, this is a determinant of the product is going to be a product of the determinant. So, determinant of U transpose equal to the determinant of I, which is 1. Okay, but these two guys are equal. Determinant of U and U transpose are the same. So, determinant of U must be 1. This is a property. Okay. Next, what can we say about eigenvalues of unitary matrices? Okay. Now let's see some sketch here. The answer here is not going to be like can we find the eigenvalues of unitary explicitly or not? All right. But what we're gonna show is that actually we know the position. We can basically tell us about locations of eigenvalues of unitary matrices. Where are they on the complex plane? Now we do the same thing. Okay, if we would like to exploit it, okay, we start with eigenvalues equation ax equal to the lambda x. Okay. Now, right now, we don't know yet whether lambda is real or complex. So let's assume that it's complex, which means if lambda is complex, x would be complex vector. Okay, operation here, any operation here that I'm going to use the star, the Hermitian conjugate operation. Okay. So this is again, this is vector equation. Okay, if I make the Hermitian conjugate and I multiply with the same guy on both sides, right? Okay, I start with the equation 1. Basically, equation 2 is obtained from making equation 1 with the inner product with ax. Okay. So what do we get on the right hand side? Of course, ax equals to lambda x, right? But lambda x star is basically lambda bar and x star x. So on the right hand side is actually modulus of lambda square multiplied by the norm of x. Okay. What about the left hand side? The left hand side, we're going to expand the quadratic form. So we're going to have x star ax. Okay. But now at some point we're going to have to use the property of unitary matrices, right? So x star a star a is going to reduce to a transpose a because we focus on real matrices, right? and next, for unitary matrices, A transpose A equals to I. So which means on the left hand side, it reduces to the norm of x squared modulus of lambda square multiplied with the norms of x. Because this guy is never 0, the norm of eigenvector is never 0. So important results, the modulus of lambda is always 1. Again, if you watch this video, can you pause the video and try to think about the location of these eigenvalues? If I sketch it on the complex plane, where are they? Okay. Of course, they rely on the unit circle. This one is one of the well-known results for unitary matrices. Eigenvalues of unitary matrices always lies on the unit circle. I think I have some example. Okay, I hope my voice goes through this video. Otherwise, okay, I think everyone is fine. Everything is fine. I'm gonna switch to. I'm just gonna illustrate by MATLAB. Huh? Okay, everyone. Oh, share. So okay, I just used an example that A is a rotation matrix, which is a special case of unitary matrices. Theta is pi over 6, and the matrix A is this. Okay. I put x is some random vector, you know. Of course, if I multiply A with x, okay, if I compute the norm of x and I compute the norm of y, just like on this screen, you see that the norm of x and norm of y, they are exactly equal. Next, if I compute the eigenvalues of A, see, they are complex values. But if I compute the absolute value or the modulus of eigenvalues, they are exactly 1. Okay, so what I show you just to confirm the property that we have just proved on mathematically. Now let's go back to the lecture. Share. Start podcast. Next, take a look at the idempotent matrix. We have a matrix A square. A is called idempotent or projection matrix if it satisfies this property. You know, A square equals A. Very simple. This is, of course, the implication from this definition is that if you compute A cubed, of course, A cubed is going to be A times A square, and of course, it's A square, and it's equals to A, right? Idempotent. If I need to make an example, of course, identity is one of them, right? Now, you're gonna find application of this matrix in the field of, you know, when you compute projection, orthogonal projection, which we're gonna introduce a little bit later. Let's take a look at the property of idempotent matrices. Okay, very simple, very easy result. Eigenvalues of A are either 0 or 1. It cannot be anything else. Okay. The second result, if A is idempotent, I minus A is also idempotent. The second bullet is not easy. It's not difficult to show, because you just need to show that I minus A square equals I minus A itself. And to show this is not hard at all. Just expand the square. Okay, I leave it as an exercise. Now let's take a look at the first property. Why the eigenvalues of A turns out to be this simple? Either 0 or 1. Okay. Now again, we always use the same tool, right? We start with the eigenvalue equation, Ax equals lambda x, where A is idempotent. Then if you want to show this result, to make it associate with the property of idempotent. So it only makes sense if you just you know like make this equation somehow similar to the property that is assumed from idempotent matrix. So the trick here is just to multiply A on both sides so that you get A square X here. But on the right hand side, because A is AX, all right, AX is, because this X is eigenvector, AX must be lambda X again. Okay, now on the right hand side you get lambda square X. What about the left hand side? At this point we haven't used property of idempotent yet, but then after you use it, A square equals X. Sorry, A square equals A. So A square X turns out to be AX. Okay, now you get equation 1, you get equation 2. These two guys are the same. You subtract 1 from 2. What you get is 0 equals lambda square minus lambda times X. And again, this X cannot be 0 because it's an eigenvector. You only have this polynomial that turns out to be the characteristic polynomial of idempotent matrix. And of course, when you solve it, the roots are either 0 or 1. Very simple. Okay, let's move it real quick. Next, projection matrix. Okay, a square matrix P is a projection matrix if and only if P square equals P. You see that this definition is actually the same as idempotent, but we just use different name. All right. What we're gonna see this kind of projection matrix is when we consider linear transformation. For example, from Rn to a subspace of Rn. Okay, and the columns of P are basically projections of standard basis vector, and that map to the subspace S. Okay, for example, P is this 1 0 0 1. Okay, if you basically check the definition real quick, so P square is multiply P 2 times, right? So you get P. Or this one also, you can just multiply and check the definition. It's satisfied. P square equals P. But when we take a look at this matrix P, what it does on the vector of R2. Okay, if I sketch the plane x1 and x2, if I have a vector x1 and x2, Px, which is y, what is it? It's actually x1 and 0. So what it does is actually you have a vector x, right? And y equal px is basically to project, right? This is a vector x1 and 0. This is actually project x on the subspace that lies on the direction of x1. This is an example. How about this matrix P? If you multiply x, y equal px is going to be x1 plus x2 divided by 2. What do you know about this? The result is that, again, what do you see in this property of the two elements in y? The two elements in y turn out to be the same. It happens to be the same. How? By the description of P. What I'm going to point out is here is that, you know, again, if you have a vector x, all right, so the projected vector y has the property that the magnitude of y1 and y2 will be the same, which means y1 and y2, the vector y lies on must lie on this straight line in R2, and this straight line has a slope of 1. This straight line is actually the subspace of R2. Okay. So these are just examples to illustrate the meaning and how the projection matrix satisfy its definition. Again, this definition has a meaning when you when p squared equals p. Okay, so y equal px, for example. If I project, sorry, if you have x, if you have y, right? If I would like to compute z, where z is given by py, which is p squared x. What do I get? By the definition of projection matrix, it's actually p squared x equals to px, right? And it's actually equals to y, which means if you would like to project the projected vector on that subspace again, it will not go anywhere. It will be the original vector y. Let me make this clear. The x is the original vector. Okay, in this example, let's say that y is going to be a projected vector. Let's say, suppose that it projected on the green line. If I project y on the green line again, where I recall to that vector as z, then from the definition of projection matrix, it shows that the results of projecting y on the subspace, on the green subspace, it will be the vector y itself. Okay, so if you apply twice on the vector in the subspace, it will give the same vector. This is a very important property of a projection matrix. However, what you're going to see a lot in application is something stronger than a projection matrix. Okay, we put some more property. Okay, a projection matrix is called orthogonal projection matrix. Okay, it requires one more property. A projection matrix is called orthogonal if and only if P must be symmetric. P equals to P transpose. Okay, so which means when one assume a projection, is already implied that you assume to have this property already, that P squared equals to P. Okay, and when you talk about orthogonal projection, this is what you require in addition. Okay, now we're gonna explain one result that you can infer from orthogonal projection matrix. The important result is that P is bounded, which means when you multiply x on P, multiply P with x, you have vector x, you have y equal px. The result is that the norm of the projected vector is always smaller, is always lower than the magnitude of the original vector. And the proof is very simple. We start with the norm of px, okay? And of course, the norm of px is this, x transpose p transpose px. Okay, but because P is orthogonal projection, so P transpose equals to P, right? Multiply with P, it gives you P squared. But P is a projection matrix, P squared equals P. Okay, from here, we apply Cauchy-Schwarz inequality. That says if you have an inner product between two vectors, okay, u and v, it always bounded by the norm of u the norm of V. Here, I just dropped the notation. What I mean is this is the two norm, all right? Cauchy-Schwarz inequality is one of the important mathematical inequalities in linear algebra. The proof is very simple. You can Google, you can read it, in 15 minutes, all right? The application is has many. This is one of them, right? You can take a look at this as U. You can take a look at this. You can consider Px as V. Of course, this inner product between two guys is always bounded by norm of Px and norm of X, which means on the left-hand side is the norm of Px, right, square. So if you just cancel one term, you get the this result, the green one, that the norm of Px is always bounded by the norm of X. Okay, now let's take a look at the orthogonal project. Okay, I forgot to okay, let's discuss a little bit more on the meaning. What does it mean by bounded property? It means that whenever you apply an orthogonal projection matrix on a vector, it will give you the projected vector on a subspace. Of course, the magnitude, the norm of the projected vector cannot be larger than the original one. For example, if I project X on this line on the standard basis, right? The projected vector is Y. And of course, the norm of Y cannot be bigger than the norm of the original X. All right. Now, let's see some example. This is a very this is a common example. This is called the rank one, a rank one matrix. If U is a vector, you compute an outer product P equals to U transpose. Okay. This is suppose we can just normalize U so that the norm of U is 1. You will see here that, of course, P equals to P transpose, right? And when you compute P square, it's going to be UU transpose, UU transpose. But when U has the norm of 1, of course, this is equals to UU transpose, which is P itself. All right. So when P has this structure, this is an example of a rank one matrix that is obtained by an outer product of a vector. This is actually an orthogonal projection on a line spanned by a unit vector. Because if you multiply P with X, what you get is that UU transpose X, right? But of course, the latter is basically a scalar. U transpose X or X transpose U. What is it? If you have two vectors, U and X, right? This guy has a unit norm. So the inner product gives the amount, right? The amount of the magnitude of X when you project it on the direction of U. So this guy is a scalar. And of course, you see Px is also, Px is a new vector that lies in the same direction as U. And what is the magnitude of that vector is determined by the inner product between X and U. Last example about orthogonal projection matrix. Okay, when A is any matrix A, that this expression makes sense, which means A transpose A must be invertible. As long as this part is invertible, A can be any matrices as long as the red box is valid. When you construct P like this, you can show that this P is orthogonal projection matrix. First, P equal to P transpose. not obvious. No, sorry, not difficult at all. Okay, p square. Let's take a look. I multiply with p again. This is p. This is p. Of course, A transpose A multiply with this guy. So it cancel out, they are cancel out, and p squared equals to p. Okay, you're gonna see this expression of this type in linear regression, because what it means is that actually interpretation is that when p has this form, all right, if you multiply p with x, it basically means that you have original vector x, all right, and what you do is you project x on the range of A. This is a subspace. This is a subspace. Depends on the size of A. Suppose A is m by n. The range of A is going to be a subspace of Rm. Okay, so the meaning of this expression, of this orthogonal projection, that it gives you a vector projected on the range of A that is closest to x. This will be discussed again when we talk about the linear regression problem. Okay, but I just put example here just to see how it looks like. Okay, we can also verify on MATLAB again. Let me switch.เดี๋ยวนะ hold on. Now I'm sharing my MATLAB screen. Okay. Now I'm just gonna construct A. Okay, my A is a tall matrix. Okay, let me make it bigger dimension than this. My A is a tall matrix. And then, okay, 10 and 2, all right? And I construct P, the matrix P, as a orthogonal projection matrix as is given in the slide. Okay, P looks like this. Okay, first of all, what do I want to show again? Okay. See, P square and P, they are the same because it is very small, 10 to the minus 16. Okay, if I check whether P is P equals to P transpose or not, again, the result is nearly 0. If I compute the eigenvalue of P, okay, see, what I get is that because P squared equals P, this is a property of idempotent matrix that we already learned that the eigenvalues are either 0 or 1. So you see the results here that the eigenvalues are either 0 or 1. You know, just confirm the theoretical result. What else do I need? Should I show? Okay. My P is hold on. My P is 10 by 10, right? So I construct a vector 10 by 1, right? And my Y is P times X. What I would like to show is the bounded property of orthogonal projection matrix. Okay, so of course X and Y's are here. This is the example. If I compute norm of X, norm of Y, see, the norm of projected vector is always smaller than the norm of the original vector. Okay, you can just keep, go on and on, because this is how we randomize. Okay, one example doesn't mean that it's always true, because to show that some condition is true or some property is true, you need to show it mathematically. What I'm doing here on MATLAB is just to confirm the result by simulation. But I can just confirm only, some cases, because there is nowhere that you can verify it on for all x, right? Okay. Now I go back to my slide again. Okay, I'm gonna go over this topic real quick. Nilpotent matrix. Nilpotent matrix is a matrix that when you compute the matrix power for some k, this matrix appears to be 0. For example, 0, 1, 0, 0, or a shift matrix. A shift matrix is called a shift matrix because if you multiply this guy with x, the result is that, try to compute it, pause the video and compute it. You're gonna get that is actually x2, x3, dot, dot, dot. And hold on, xn, xn. Shift it, you shift it up. Okay. So if you, hold on, there's gonna be, actually the last row should be 0, I guess. Yes, this might be a typo. All right, the last row should be 0. Okay, so the last entry should be 0. Okay, if you just for example 0, 1, 0, 0, if you just compute the square of this guy, you get 0, 0. In this case, a is nilpotent, where k is just 2. Okay, you can try with the shift matrix. If this guy is n by n, how many times you need to compute, what is the power of a to the k, what k is, until, a to the k is 0. Nilpotent matrix will be shown when we discuss about the deadbeat control in linear systems. It's very simple. Characteristic equation of nilpotent matrix is that lambda to the n is 0, because again ax equal to lambda x. If we multiply a on both sides, you get a squared x equals lambda square x. Okay, and if you keep going on and on, you get a to the power of kx equals to lambda kx, but then the left hand side is 0, right? So which means the all the eigenvalues of nilpotent matrix are 0. Where the matrix doesn't have to be 0 itself, but all the eigenvalues are 0. Last one, I would like to end the lecture with this special group of matrices, positive definite matrix. Okay. These find a lot of applications. Quadratic form in X often parameterized by a PDF matrix. Okay. The concept of PDF matrices allow us to quantify the like positiveness of a matrix by taking a look at the a scalar quantity that is obtained as a quadratic form in X. Okay, so let's take a look at the definition. When we talk about positive semi-definite property, we actually focus on the set of symmetric matrices, and we're going to use this notation. A positive semi-definite. Okay, and you see this inequality is curly. This is not the same as this, right? All right. We have this this notation. We call in short PSDF, positive semi-definite. Okay. If you consider a quadratic form in x transpose AX, and if you take a look at the dimension, x transpose is 1 by n, so the whole thing is actually 1 by 1. You take a look at this scalar, and whenever this scalar quantity is bigger than 0, is always non-negative. Whenever x is any vector in Rn, then we say by the definition A is positive semi-definite. And of course, a very minor distinction, we call A positive definite, and we use this notation without the inequality. If this scalar quantity is always positive for all non-zero x. Okay, now let's take a look at the definition. For example, if A is this guy, all right, A is this guy. Let's take a look at the quadratic form of x parameterized by A. So quadratic form of x, I hope you learn how to calculate this quickly, because we often encounter this quadratic form, several times. All right. So when you multiply x transpose AX, of course, x1 will be multiplied with this and with this x1, so you get x1 square. And of course, x2 will be multiplied by 2, and x2 you get 2 of x2 square. What about this crossing term? This crossing term This crossing term is where you multiply x1 with -1 and with x2. All right. But because you're going to have this multiplication twice, because from the upper part and the lower part, and that's why you have minus and with the factor 2. Okay. So try to compute this quadratic form at home, at your own time. You're gonna need this a lot. Okay. Here, in this example, quadratic form turned out to be this. If we want to verify whether A is positive semi-definite or not, we need to check whether this guy is always non-negative for all x by using completing square. Okay, so I just completing square x1 minus x2 square, and I just add the remaining term just to make it equal to the previous line. Everyone know how to complete a square, I hope. So at the last line, when you complete the square, you know that it turns out to be the sum of two non-negative terms. Whenever x1 and x2 are any vector, this guy is always non-negative. And I would like you to make a distinction between these two words, non-negative and positive. Non-negative means it could be 0, right? But for positive, it means that it has to be strictly greater than 0. So in this example, A is positive semi-definite. Okay. The matrix A, there's many ways that you can make an example of indefinite matrices. For example, 1, 2, -2, and -2. I hope this example works. Okay, so x transpose AX is going to be x1 square plus 2x2 square minus minus 4x1 minus minus 4x1, x2. And again, if we just complete the square, now we would complete it in the way that, you know, minus 2x2 square, right? But again, what is the remaining term? What is the remaining term? This is what we get 4x2 square, but we originally have 2x2 square. So you need to subtract minus 2x2 square. Okay. Here in this example, you see that when you arrange the expression, you see that you cannot tell whether this guy is always non-negative. You cannot guarantee. For example, I can come up with x which is equals to 1 and 10, for example. I hope it works. X transpose AX is gonna be what is it? 1 minus 20 square minus 2 times 100. Is it negative or not? Oh, it's positive, so this is not a good example. Okay. I'm just gonna come up with some x. Okay, why don't I get x is 0, right? Not a good example again. Okay, never mind. I hope you can make an example on at your own time. All right, but my conclusion here is that this guy is not always non-negative, which means you cannot conclude that this guy is positive semi-definite. So whenever we have a conclusion like this, we call that A is indefinite. A is indefinite. Okay. Let me think again. Maybe I can make an example. Okay, yes. Okay, in this particular example, if I make a choice, special choice that x is 5 and 2, of course, x transpose AX is going to be 5 minus 4 square minus 2 times 4, right? Which is, of course, obviously minus 7. This shows that there is some x in R2 that x transpose AX is negative. So A cannot be positive semi-definite. Okay, now let's come back. So once you know the definition, okay, of positive semi-definite, now I would like to stress one important result that that allows you to check this property easily on computer. Okay, so because when we check sometimes when A is given, okay, you would like to have a practical condition to check this property either by computer or by the analysis. So it depends on the structure of A. Now we give you a very important result that checking the positive semi-definite condition of A is the same thing. All right, necessary and sufficient condition. This is the same thing as checking whether all the eigenvalues of A are non-negative or not. Okay, to show this is very straightforward. Now let's take a look. Do I need a space? Okay. After. So A is bigger, A is positive semi-definite if and only if lambda I of A all the eigenvalues of A are positive, are non-negative. Okay. Oh, sorry. So to show the to show the necessity, maybe show this way is simpler. Let's show this. So one way, first way is that if all the eigenvalues are non-negative, we can immediately imply that A is positive semi-definite. How? Because again, to show that A is positive semi-definite, we need to examine this property. But because when A is positive semi-definite, you can always use this eigenvalue decomposition that we just explained previously, because A is symmetric. There's a delay on the screen. Okay, and then we call this guy Y, right? Y transpose dy. Therefore, you see this. You can see this immediately, that because this guy is the sum of the di yi square, where di is actually lambda I of A, right? So if all the eigenvalues are non-negative, it's obviously see from this expression that the whole thing will be non-negative. Okay, what about the other direction? If A is positive, then why the eigenvalues of A are all non-negative? Okay, with the same reason. Okay, this is a given statement. All right. Let's take a look at this quantity again. A transpose AX equals Y transpose DY, and equals to lambda 1 Y1 square, lambda 2 Y2 square, right? Lambda n yn square. Okay. So when this guy is given, we can say that, of course, to conclude that lambda I are non-negative, right? Then it's possible. Then it's possible to show that there are going to be some x such that y equals EI. When y equals EI, it means that this is a standard unit vector that, you know, all the components are 0 except 1, where 1 occur at the I position. This is a standard unit vector. So when there exists a vector x like that, you know, implies to the vector y is standard unit vector, you see that x transpose AX equal Y transpose DY equals, when you substitute this into on the right hand side of this equation, it turns out on the right hand side to be lambda I. Okay, and because this guy is given that A is positive, it means that on the left hand side, you know that it is bigger than 0. Okay, and of course, why? This is to further explain that because y is equal to what? Y equals U transpose X, right? But because U is invertible, okay, you require y to be, you want the freedom to choose y as a standard unit vector. The answer is, of course, to confirm that you can always do that. There's going to be always a vector x that allows you to choose such y, because your x is actually uy, right? Like the inverse operator. It's actually U of EI, okay, which is UI. You want to show that if A positive semi-definite, all the lambda I must be positive. All the lambda I's are non-negative. Okay, in order to show that, you say, oh, you are allowed to choose y as standard unit vector. Then the reason why you can always do that, because you always find x that equals to the column I of the matrix U, that gives you the vector y as ei. Okay, so this shows that the eigenvalues are non-negative are both sufficient and necessary condition of positive semi-definiteness of A. Okay, I have one more practical condition, that all the principal minors of A are non-negative, but I'm not going to prove it here. You can read it from any matrix analysis book. Principal minors of A means if you have a matrix A, you start with the 1-1 entry. This is the first principal minor. The second principal minor is you take a look at the 2x2 block and you find the determinant of this guy. The next leading block is of course the matrix, the main 3x3 leading block. Okay, the principal minor is actually the determinant of this leading block, and you keep going this. You keep doing this, computing the principal minors. If all the principal minors are non-negative, A is positive semi-definite. Last, I would like to finish this video quickly. From this property, I would like to point out again here that to check the positive semi-definiteness of A in practice, if A is, just obtained from data that, doesn't have to be integer, it's just A that you compute from previous steps or something. The practical way to check the positiveness is to compute the eigenvalues. All right, but when A has a special structure, like for example, when A is triangular, or maybe A is a toplet metric, or A is a band metric, it's very interesting to check the positiveness of A from the definition, which means you just characterize the quadratic form. Okay. Now we like to end the video by giving you one important result again, that the positiveness property is not changed by what's so called congruent transformation. If A is non-negative, is positive semi-definite, if you multiply B is any matrix, all right, such that the multiplication makes sense. If you multiply B and B transpose on both sides, or you can also do this as well, the results of the multiplication is also positive semi-definite. Okay, the transformation from A to the new matrix like this, we call it C. This is called congruent transformation. So one simple statement: congruent transformation doesn't change the positive semi-definiteness of A. The proof is very simple, because, okay, you have the matrix C, B, A, B transpose, right? Given that A is positive semi-definite, if I would like to examine the positiveness property of C, of course I do it by the definition. I compute the quadratic form, right? So it's going to be X transpose B A B transpose X. But again, I can also take a look at this part as a new vector Y, right? So it turns out it reduces to Y transpose AY. On the left-hand side, I'm going to examine this property for all X, right? But it turns out to this result that I know that it always non-negative because A is positive semi-definite. This implies that my C is positive semi-definite. Okay, from this result, it it further imply that if I have the matrix A, all right, that is positive semi-definite, of course, I have diagonal terms and the diagonal term, blah, blah, blah. From this property that whenever I apply congruent transformation, the positive semi-definite is still preserved. So if I pick B to be the matrix I and 0, all right, so B transport is going to be, suppose my A is partitioned into 4 blocks. Okay, I hope everyone understand the block matrix partition. Okay, A11 and A22 are square blocks. Okay. So for example, if this guy is 2 by 2, this is 3 by 3, the whole thing of A is 5 by 5, all right? The matrix I here is the size of 2 by 2, for example. So the result of the multiplication, if you just multiply it out, okay, it will be just simply A11. There's a delay. Okay, so it means that from this property, it means that if I choose B to be I0, I can further imply that my 1 block has to be positive semi-definite. Go the same way, it goes the same way. If I choose B to be 0 and I, okay, you take a look again, just verify yourself what would be the size of this identity that the multiplication is valid. So B transpose is going to be A22, and again by this property that we just derived, you can further conclude that A22 must be positive semi-definite also. This means whenever you have positive semi-definite matrices, all the main diagonal blocks have to be positive semi-definite. This is one important result. All the leading blocks of A are positive semi-definite. And of course, when you talk about the leading blocks, a special case is of course the diagonal terms of A are all non-negative. Okay. Next, if you have two positive semi-definite matrices, the sum is also positive semi-definite. This is not hard at all. I'm not going to prove it. I hope you can verify this fact yourself. Let's take a look at the last one. Whenever you have a positive semi-definite, it allows you to talk about, something that gives you the square root sense. For example, everyone knows that, a scalar of 4 is actually 2 and 2, 2 times 2, or it can be either, minus 2 times minus 2. And we call 2 as a square root. We call minus 2 as a square root, right? So matrices has the same sense. Like you have a matrix A, somehow you can talk about the square root thing in terms of matrices. And we use this notation like A1/2 or square root of A. You would like to come up with this matrix that, it multiplies, itself together and it gives the matrix A. Okay. For a scalar that has a square root, that scalar itself has to be positive. For the matrix, again, we have the same analogy. If A is positive semi-definite, then we can talk about its square root. Okay, so how? Let me make it explicitly. What we know from the analysis is that if A is symmetric, A has this decomposition. Okay, where D is diagonal matrix that actually the diagonals of D is eigenvalues. But what we know, this is what we know from symmetric property. But what we know from being positive semi-definite is that all the eigenvalue must be non-negative, right? Then how about we can actually factorize it, right? D actually is factorized into multiplication of two diagonal matrices, and actually the diagonal terms are the square root of eigenvalues. How about so this shows that for diagonal matrices the concept of the square root is very simple. Just take the square root of the diagonal terms. Okay, now I can write d1/2 the square root of d. Okay, now I have used two properties of A, symmetric and positive semi-definite. All right, then next, what I know about the eigenvalue of A is that U is orthogonal, right? Orthogonal. So I can just not only orthogonal, I mean the eigenvalues of, sorry, the matrix U that contains the eigenvectors of A, they are unitary. U transpose equal to U transpose U equals to I. So I can just basically I can just add this green term. I can just add this because it's equal to I. But then after doing this, you can see that it turns out to be basically just, it looks like just two matrices multiplied together. So I can call this guy A1/2 and A1/2. And this gives me just one way of defining a square root of A. So I just define A square root as U d1/2 U transpose, and then I get the square root of A. Of course, there's another way to compute this because the matrix U can be scaled in many ways. You can explore this option further from any other reading that you might see in the future. Why do we need this? We're gonna see the application of this when we talk about maybe I cannot think of an application right now, but in the analysis of linear system control theory, a random process, you're gonna come back to, you know, application of positive semi-definite matrices again and again. So I hope you I hope you understand, okay, and refer to these important statements, these important properties of positive semi-definite. And I would like to end the lecture of today. All right. If you have questions, of course, we discussed in the online class session. Stop.